Hello and welcome to our live coding example for fixing caps in time series. This was written in MATLAB 2020B and requires the curve fitting toolbox for the fit function because it uses a spline fit. And so this is for fixing time series which have an artificial cap. So many times, many things go wrong when you deploy sensors in the field. And one of the things that can go wrong is the time series can have an artificial maximum, right? So the field values that you're measuring, say you're measuring temperature or whatever, you're measuring temperature, say, and the time series is doing whatever fluctuations based on the temperature, of course, and maybe it goes up to a certain maximum value and then just stays there, right? Artificially, in a way that is clear that is not actually what happened to the temperature field, but for whatever reason, you get a near constant value, maybe with some noise. And so we're going to apply this to some data which actually doesn't have anything wrong with it, which I have artificially damaged, just so that we can check our our method, right? So for tutorial purposes, I want to be able to confirm that my code does what I intended it for it to do. And so we're going to use Monterey Bay kinetic energy data. This was a data set which first appeared in, I think it was first appeared, but anyway, it was studied in Walter et al. 2016, which is observations of nonlinear internal waves at a persistent coastal upwelling front, which appeared in coastal shelf research. And so, great paper. I highly encourage you to read it if you're into internal waves at all. But we're gonna look at the kinetic energy from there, and I've artificially damaged it, as I've said. And so we're going to just fire up the code here and show you what it does. So these are the indices. I've saved the indices of the series that were damaged, and so I'm going to select series 5, and I'm going to just fix one cap. That's fine. Okay, so I'm going to come along here. Let's zoom in on this cap right here. And basically you can see that it kind of fluctuates, and then it comes up to this kind of stable level, and it continues to fluctuate and then comes back down again. So this doesn't look very physical. It doesn't look very plausible. You can see in the top here that except when it reaches this kind of maximum level, these other ones have kind of a spiky look to them, right? They're not constant capping, except that it seems that the sensor itself looks like it has some kind of noisy cap, which you can see across the entire time series. Well, that's because that's how I damaged it, and I damaged it that way because that's what you see sometimes in field data. So let me come along here, and I'm gonna say, well, this whole thing is the cap. I'm not sure about any of this stuff, so I'm gonna click here, and I'm gonna come all the way over here and click here. Okay. Now it's busy. What is it doing? Well, it comes along and it removes that cap, and then it fits a spline to the rest of the time series. And of course, there's a fair amount of points in the time series, so it takes a minute. It does a smoothing spline. It's not looking to go through every point, but to smoothly transverse. And so this gives us a way to overshoot what is missing, which is the cap, because we removed it, and apply an artificial cap. Okay, so this is a good example. So you look at this this figure and you say, well, actually, let's look at this figure first. Let's go through what the actual algorithm did. If I zoom in here, you'll see that the green is the smoothing spline, and it's passing through the points. And you'll see that at the cap, the spline was not applied to pass through these points. These are the points that we removed, and the spline goes through all the other points, right? So if I back out again, you can see that the spline is through the entire time series, and it is missing near is missing the points in the cap, and that's what creates the overshoot. This noise curve here, I'll explain more later, but basically, this noise curve is the difference between the green and black curves, and tells you how much this amount of fluctuation here gives me a way to add in the noise that you see up here, right? So the cap I've added here isn't just the spline, it's the spline plus some noise. Okay, well then let's consider the fit I've attained here. And let's come over here. This is already zoomed in. This is just looking at the cap, and you go, well, it's not that great because look how high this spike goes up. Okay, but here's where we get to the kind of the meat of the message here, is that there is no free lunch. If you damage these caps, I have no idea what was there. I can surmise what was there. I can attempt to maybe let's say that if this was one sensor in a thermistor chain and I had information above and below, and then okay, well maybe I can interpolate that. I can interpolate across and fill in what was missing. But that's just saying that I had sensors that didn't fail. In many cases, when you have a deployment, you don't have nearby sensors. You have one sensor cluster. And in that case, if nothing else is nearby, that is lost forever. That data is gone. And so you can argue all kinds of ways of how you should fill it in or what you should do. And in particular contexts, if you have the expertise to say within a reasonable depth what should be there or so on, okay, well then argue that way. This method is for the much more blunt case where you just don't know. You have no idea. And so the main point I want to give you is that this with the blue cap is more physically plausible than this. Is it perfect? Absolutely not. But it's better. And the idea here is that if you have a lot of data that's messed up and in this way with all these caps that are artificial, you can come along with this method and apply it and get something that is much more physically plausible. Will it be perfect? Well, frankly, if it's damaged data, you won't know if it's perfect. But it will be better than it was. And that's what this method is about. So that's the capping method. Hope you enjoyed it, and play around with the code by all means. I'll just point out that there's a lot of stuff going on here. This right here is the spline fitting method. This is what you need the toolbox for right here. This is the noise, and this is why it's in air quotes, is I found the standard deviation of the difference between the data outside the caps and the spline outside the caps. And so when I go down here to plot it, I plot the data minus the spline. And so that's why right here, this is just the difference of the two curves everywhere except the cap, right? Then when I look at the standard deviation, that's just to make sure that I can apply some reasonable amount of noise to it. Okay, so that's that. That is the spline fit method of fixing caps in time series. Thanks for watching.